All right, today we're going to crack the code on algebra, but maybe not in the way you remember from school. We're going to treat it like a secret language that once you learn the rules, lets you solve some really incredible puzzles. Okay, let's dive in.
So let's just start with this one simple idea. What if we stop thinking about algebra as scary, complicated math and start thinking of it as a language? A language with its own vocabulary, its own grammar, and its own way of putting sentences together.
Every language has words. In algebra, our words are basically numbers and variables. Numbers, like 5, they're fixed. A 5 is always a 5, no surprises there. But variables, like the x you see all the time, they're flexible. Think of x like a mystery box. It's just a placeholder that can hold any number. And that flexibility, that's what makes algebra so powerful.
So what happens when you combine these words, the fixed ones and the flexible ones, using your basic operations? Well, you get an algebraic expression. This is basically our version of a phrase. It's not a full sentence yet because there's no equal sign, but it's a complete thought.
Okay, so we've got our vocabulary. Now we need some grammar, the rules that tell us how all our new words are supposed to interact. And in algebra, one of the most fundamental sets of grammar rules is all about powers, or as they're sometimes called, indices. And the core idea here is, honestly, it's incredibly simple. A power, like x to the third, isn't some complex, scary thing. It's just shorthand. It's a lazy but really efficient way of writing x times x times x. That's it. It's really just a simple counting tool.
And that simple idea of counting gives us these essential grammar rules, the laws of indices. As you can see in this table, they're pretty straightforward. When you multiply, you just add the powers. When you divide, you subtract them, and when you raise a power to another power, you multiply them. This is basically your cheat sheet for becoming fluent.
Okay, vocabulary? Check. Grammar? Check. Now we can start forming more complex ideas. This is where expanding and factoring come into play. Just think of expanding as building longer, more descriptive mathematical sentences, and factoring as finding the short, concise summary of that sentence.
This visual gives us a great way to understand expansion. Just imagine a rectangle with a length of x plus 3 and a width of x plus 2. Well, expanding the brackets is the exact same process as calculating the total area of that rectangle. It makes a pretty abstract idea way more concrete.
So how do we actually do it? Let's walk through it, step by step. First, you distribute the x into the second bracket, and then you do the same with the 3. After that, you just clean it all up by combining the similar terms, the 2x and the 3x, to get your final answer. It's a methodical approach, and it always works.
But you knew there had to be a shortcut, right? Of course there is. This is the pro-level move. FOIL is just a simple way to remember to multiply everything correctly. You multiply the first terms, the outer terms, the inner terms, and finally the last terms. It gets you to the same answer, just a little bit faster.
All right, now let's slam it into reverse. If expansion is building the sentence, factorization is breaking it back down to its core parts. We're taking that long expression and trying to figure out which two brackets, when you multiply them, created it in the first place.
The key here is really just a little puzzle. We need two numbers that multiply to get that last term, 6, and add up to get the middle term, 5. So in this case, it's 2 and 3. Easy enough. Once you have those, you can rewrite the expression and group the terms. And you'll see this common phrase, x plus 2, just sort of appears. Factor that out, and you're left with the original brackets. It's the perfect reverse of what we did just a minute ago.
Now, in any language, there are common phrases or idioms that fluent speakers use all the time just to save effort. In algebra, we call these identities. They're patterns that show up so often that memorizing them is one of the real keys to getting good at this.
And here they are, the three most important ones. You've got the perfect square for a sum, the perfect square for a difference, and my personal favorite, the difference of squares. You should honestly treat this slide like a set of flashcards. Knowing these patterns by heart is a total game changer.
So you might be asking, why bother memorizing these? Well, they're shortcuts. If you don't spot the pattern, you're stuck taking the long, winding road. But if you see one of these identities, you can just take the direct path and instantly write down the answer. It is the ultimate time saver.
Okay, it's time for a test. Let's take all the vocabulary, grammar, and those common phrases we just learned and apply them to a challenge problem. This is where you get to see how powerful your new language skills really are. So here it is, a classic Olympiad-style problem. Factorize x to the power of 4 minus 16. Now I get it. At first glance, this might look pretty intimidating. But what if we rewrite it in a way that might look a bit more familiar? Let's just reframe it a bit. X to the fourth is really just x squared squared, and 16, well, that's just 4 squared. Now, does that structure, something squared minus something else squared, ring any bells? It should look exactly like one of our must-memorize identities. And there it is, the difference of squares. This little identity is the key that unlocks the entire problem. The pattern is a perfect match.
So just by applying that rule, we can instantly factor our expression into x squared minus 4 times x squared plus 4. That is a huge step forward, and we did it in a single move, all thanks to that identity. But here is the crucial question. Are we actually done? One of the biggest mistakes people make is stopping too early. So take a closer look at that first term, x squared minus 4. Does that look familiar too?
Of course it does. It's another difference of squares. It's x squared minus 2 squared. So we can apply the exact same identity a second time. And that gives us our final, completely factored answer, x minus 2 times x plus 2 times x squared plus 4. How cool is that?
And that problem right there perfectly illustrates a key lesson. A partial factorization is a really common trap. So you should always ask yourself, can I go one step further? In this case, that one final check made all the difference.
So, there you have it. We've learned the words, the grammar, and some of the key phrases of this language of algebra. We've seen how these tools let us build up expressions and break them back down. So the real question is, now that you know the basics of the language, what are you going to build with it?
Hey everyone, and welcome! Today we are diving deep into a topic that is, it's the absolute backbone of algebra, polynomials. We're going to break them down, build them back up, and I promise, by the end of this, you'll see them not as some scary problem, but as a fun puzzle you absolutely know how to solve. Okay, let's get into it.
But before we get tangled up in all the formal stuff, let me ask you this. What if you could figure out complex algebra just by picturing it as Legos? Seriously. Stick with me here, because this one simple idea, it's going to make everything else just click. And that brings us right to our first section. We're starting there, with the most intuitive, visual way to really get what a polynomial is. Think of it like you're building something with math.
Okay, let's make this real. See a polynomial like 3x squared plus 2x plus 1? That's not just a random string of symbols. No way. Using our Lego idea, just imagine you've got 3 of the big x squared blocks, 2 of the medium-sized x blocks, and 1 of those tiny little single blocks. That is it. A polynomial is just a pile of different-sized pieces all added together. All right, so we've got the Lego idea down. Now let's just put on our official mathematician hats for a second. Formally, a polynomial is just an expression that looks like this. The rules are actually pretty simple. The exponents, the little numbers up top, they have to be whole numbers, so 0, 1, 2, 3, and so on. And the coefficients, the numbers out front, they can be any real number. It's just the official language for our Lego set. And to speak this language, you really only need 3 key terms. The degree, that's just the size of your biggest Lego block, the highest power of x you see. The leading coefficient is just how many of those biggest blocks you have. And the constant term, well, that's your pile of the smallest single unit blocks. See? Simple. Okay, so we know what the blocks are. Now for section 2. What are the rules of the game? How do we actually play with these polynomial Legos? Turns out it all comes down to a few really simple moves. Adding polynomials is, this literally, it's just sorting your Legos. You find all the blocks that are the same size, those are your like terms, you put them in the same pile, and then you just count how many you have in each. You can't add a big x squared block to a medium x block, right? You just group the similar ones together. That is all there is to it. Now, multiplication is just a tiny step up. The magic word here is distribution. You just take each piece from the first polynomial and multiply it by every single piece in the second one. So for something like x plus 2 times x plus 3, first you multiply the x by everything in x plus 3, and then you multiply the 2 by everything in x plus 3. After that, you just tidy up by combining your matching Lego blocks, just like we did with adding. And now for the really fun part. Seriously, forget all that tedious, long division you had to do. In section 3, we're going to learn a brilliant, super powerful shortcut that lets you find the remainder of a division problem in like a single step. This is a total game changer.
And this right here, this is the magic wand. It's called the remainder theorem. It basically says if you want to know the remainder when you divide some polynomial f of x by a simple little thing like x minus a, you don't actually have to do the division at all. You just plug that value a into the polynomial. The remainder is simply f of a.
Let's see this thing in action, okay? We need to find the remainder when 2x cubed minus 3x plus 1 is divided by x minus 2. Forget long division. The theorem tells us that our a value is 2, so all we have to do is calculate f of 2. We just pop a 2 in everywhere we see an x. And boom, the answer is 11. That's it. No long, messy work. We just calculated f of 2, which is 2 times 2 cubed minus 3 times 2 plus 1. So that's 16 minus 6 plus 1, which gives us 11. That is the remainder. It's that fast.
But why on earth does this little magic trick work? Well, think about it like this. Any polynomial, f of x, can be written as the thing you're dividing by, x minus a, times some answer, plus whatever is left over, the remainder. Now, what happens if you plug a in for x? That whole first part, a minus a times the answer, that just becomes 0. So all you're left with is the remainder, which means f of a is the remainder.
So what happens when that amazing shortcut gives us an answer of 0? Well, that is a very special clue. It's like finding a secret message, and it leads us directly to section 4, where we uncover a master key for factoring these things.
This is the factor theorem, and it's the next logical step. It says that if you plug in a and you get 0, well, that means there's no remainder. And if there's no remainder, it must mean that x minus a divides the polynomial perfectly. In other words, x minus a is a factor.
So let's connect the dots here, because it's super simple. The factor theorem isn't some brand new idea, it's just a special case of the remainder theorem. The remainder theorem tells us the remainder is f of a. The factor theorem just says, hey, if that remainder happens to be 0, you've unlocked something awesome. You've found a factor.
So how do we actually use this? Okay, say we've got this polynomial, x cubed minus 4x squared plus 5x minus 2, and we're wondering, is x minus 1 a factor? Instead of doing all that division, we just use our key. We check f of 1. So we plug in 1, and we get 1 minus 4 plus 5 minus 2, which equals 0. The remainder is 0, which means ding, 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 we've unlocked a factor, x minus 1. All right, we have all the tools, we know what polynomials are, how to work with them, and now we know how to find their factors. In this final section, we're going to put it all together to solve the ultimate puzzle, finding a polynomial's roots. First off, what are we even looking for? Well, the zeros or the roots, they're just the special values of x that make the whole polynomial equal to 0. And here's a cool way to picture it. If you were to graph the polynomial, the roots are the exact spots where that curve crosses the horizontal x-axis. So how do we find them? We use our factor theorem kind of in reverse. Let's take this polynomial, x cubed minus 3x squared minus 4x plus 12. We start by just testing some simple numbers. Let's try plugging in x equal 2. We run the numbers, and we get 0. Perfect. That means x minus 2 is a factor. And now that we have one piece of the puzzle, we can divide it out and find the rest. And once it's fully factored down like this, the zeros are just staring you right in the face. What makes each little piece equal to 0? Well, if x is 2, that first part is 0. If x is 3, the second part is 0. And if x is negative 2, the third part is 0. And just like that, puzzle solved. The roots are 2, 3, and negative 2. And hey, here's a quick pro tip. When you're on the hunt for that first root, please don't forget to test negative numbers, like that minus 2 we just found. It's a super common mistake. And once you find one factor, don't just stop. Keep going until you've broken the puzzle down into all of its simplest pieces. And that brings us to the end. We've gone all the way from Lego blocks to solving for roots. So I'm going to leave you with one final thought to chew on. This is a classic challenge problem idea. If a polynomial has nice integer coefficients, and you know one of its roots is a weird irrational number, like 1 plus the square root of 2, there is another root that it must be hiding. What is that other root, and more importantly, why does it have to be there? Something to think about. Thanks so much for watching.